When solving a problem involving a projectile, we know that how you move in the x direction is completely independent of how you move into the y direction. But here's the big problem-solving hint. We need to be able to link these two things together because often we are given information about one dimension, perhaps the y dimension, and then asked a question about the x dimension. Now from last lecture, we know that the only thing that links these two dimensions together is time. So the problem-solving hint that I have for you to solve any kind of problem involving a projectile is to use the y dimension to find that time in the air. Then solve the problem. Okay, so we're always going to find the time in the air first, and then hopefully that is going to allow us to solve the problem. Here's what I mean by this. Let's look at exercise 1. Fred throws a baseball 42 meters per second horizontally from a height of 2 meters. How far will the ball travel before it reaches the ground? This is a very common word problem, and if anything, it sounds a lot like the word problems that we got back in Unit 3 when we studied acceleration. And if you remember back in Unit 3, we always made a knowns table. So we're going to make a knowns table again, but I'm going to make one modification to this knowns table. I'm going to separate my knowns into knowns that are for the x direction and knowns that are for the y direction, because we know that x and y are never going to mix. So when it says that Fred throws the baseball 42 meters per second horizontally, that's telling me that my velocity in the x direction is 42 meters per second. It's thrown from a height of 2 meters. A height is really telling us something about the displacement in the y direction. So I'm going to call that delta y, just so I remember it's the y direction. Now this baseball is going to go from 2 meters down to the ground, so it's falling 2 meters. So I'm going to call that negative 2 meters. How far will the ball travel before it reaches the ground? Well, that's really asking me, what is my delta x going to end up being? This is all the information that's given to us in the problem. However, these are not the only things that we can put into our knowns table. Just like in Unit 3, we had to read for some implicit information, things that the problem did not have to specifically tell us, but that we knew was going to be true anyway. So, for example, things like, since we are flying through the air, we know acceleration is going to be negative 9.8 meters per second squared. That's not something that the problem needs to specifically tell us. That's something that we already know. And because this thing is being thrown horizontally, we also know that the initial velocity in the y direction is 0 meters per second. Right when Fred lets go, we're not moving up or down at all. So our initial velocity in the y direction is 0. Now, something that we don't know is we don't know the time in the air. And because time in the air is both an x quantity and a y quantity, I'm going to put a delta t equals question mark for both of these. Now when we look at the knowns table and we look in the x column, we see that we have one thing we know and two things that we don't know. And we can't solve for two things that we don't know, so I think we're going to have to leave the x column alone for now. Instead, let's look at that y column. In the y column, there are 3 things that we know and 1 thing that we don't know. And you know what? I definitely think I remember an equation that involves all of those things. Delta y equals vi delta t plus 1/2 a delta t squared. That is an equation that involves all 4 of those things in my y column, and I can use this equation to help me find the time in the air. So I'm going to put in negative 2 meters for my delta y. My initial velocity was 0, so that goes away. And then I know that my acceleration is negative 9.8 meters per second squared. And I'm going to solve for this delta t. So from here, it's just algebra. And when I do the algebra, I find that my time in the air ends up being 0.638 seconds. So I can add that to my knowns column. My delta t is really 6.638 seconds. And it goes in both columns because, again, time is the only thing that links x and y. Now, if I look at my x column, look at that. I now have two things that I know and one thing that I don't, and that thing that I don't know is the thing that the problem is asking for. So let's just go ahead and use delta x equals v delta t and use everything that we have in our x column. So delta x is equal to 42 meters per second times 0.638 seconds. And then we find that our delta x ends up being 26.8 meters. So Fred is going to throw that baseball 26.8 meters. Do you see how this example problem showed us what to do with this problem-solving hint? The first thing we did is we used the y dimension to find the time in the air, and then once we had the time in the air, it was really easy for us to solve the problem. Let's see if that same hint helps us here in exercise 2. A movie director is shooting a scene that involves dropping a stunt dummy out of an airplane and into a swimming pool. The plane is 125 meters above the ground, traveling at a velocity of 20 meters per second to the right. The director wants to know where in the plane's path the dummy should be dropped so that it will land in the pool. So here, I'm going to maybe down where there's a little more space, I'm going to draw a picture of this just so that we can visualize what's going on. There's our plane, and what we have is we have a pool. And we want to know if this plane is going to drop a dummy, that dummy is going to be a horizontal projectile that we want to eventually have land in the pool. So the question is, where do we need to release the dummy so that it will end up landing in the pool? That really is asking us, what is our delta x going to be? All right, well, let's do like we did last time. Let's make a table of knowns. So we'll make a knowns table for x and for y. Reading this, we see that our change in height is going to be negative 125 meters since they are dropping that dummy from high in the air and it's going to hit the ground. The plane is traveling at a velocity of 20 meters per second. And it is also in the x direction that we want to solve for the displacement. Yet again, we are only explicitly given 3 things to put into our knowns table, but we also know things like acceleration is going to be negative 9.8 meters per second squared. This dummy is going to be a horizontal projectile, so the initial velocity in the y direction is going to be 0 meters per second. And we know that we probably are going to need to solve for the time in the air. Now, have you noticed that we have the same 3 variables in our x column, v, delta x, delta t, and we have the same 4 variables in our y column, delta y, a, vi, and delta t. You should always make sure that you have the 3 variables in the x direction and these 4 variables in the y direction before you start any problem, because we're going to always need all of these things. Let's start by looking in the y direction and using everything we know about the y direction to solve for time. We're going to use that same equation that we used in example problem number 1. We're going to use delta y equals vi delta t plus 1/2 a delta t squared. Our delta y is negative 125 meters. The initial velocity in the y direction is 0, so that goes away. Our acceleration is acceleration due to gravity, negative 9.8 meters per second squared. And now we are going to solve for delta t. It is all algebra. So once we do the algebra, we find that our change in time is going to be 5.05 seconds. That's how long it takes for this dummy to fall. So let's add that to our knowns table, 5.05 seconds. And it gets added to both columns. Now we can look at the x dimension, and we can solve that problem by using delta x equals v delta t. We can substitute in 20 meters per second as our velocity. We can substitute in 5.05 seconds as our time, and then we find that we're going to have to drop this dummy 101 meters before we get to the pool. There we go. Not too bad. Let's do part B. Find the instantaneous speed of the dummy as it hits the water. Now, what we mean by instantaneous speed is what I was referring to last lecture when I drew these red lines on the path of a horizontal projectile. If you remember from last lecture, we talked about how the horizontal velocity is always going to stay the same, and how our y velocity is going to get larger and larger and larger the longer that we fall. And when we add these two independent velocities together, we end up getting the total velocity. So the velocity that is both x and y, we call that maybe the total velocity. But a synonym for that would be the instantaneous velocity. So the problem that we are dealing with right now is asking us to please find that total velocity that is tangent to the curve. And I'm going to abbreviate it as v total. We need to find this. Now, this is a little bit different than the last two problems that we've done. We don't really have a time that we need to solve for. We don't really have a delta x that we need to solve for. Instead, we're trying to find a velocity. Well, if you remember, anytime we have something pointed in a crazy direction, we can always break it up into its x and its y components. So if we take that total velocity, we break it up into its horizontal component, and we can break it up into its vertical component. Now we already know what this horizontal component is. We remember that that is 20 meters per second, because that's how fast the dummy is moving in the x direction, right? We have that in our knowns table. Now we don't know the y velocity right before he hits the water, but if we could figure it out, then we could use Pythagorean theorem to then figure out that total velocity. Now, if we go back to our Venn diagram has every single algebraic tool that we could use to solve projectile problems. And it appears that right now we're looking for some kind of a final velocity before we hit the water. We know the acceleration, we know the time it takes for us to hit the water, and we know that we start with a velocity of 0. So I think we should use VF equals A delta t plus VI in order to solve this problem. All right, I'm going to switch back to black. Let's use VF equals A delta t plus VI. So our final y velocity, and I'm going to call it Vy instead of VF, it's going to be negative 9.8 meters per second squared times 5.05 seconds for us to fly through the air, plus our initial y velocity of 0 meters per second. So that tells us that our y velocity right before we hit the ground, or sorry, the water, is going to be negative 49.5 meters per second. So now we know that this side of our triangle is negative 49.5 meters per second. And since we are looking for the hypotenuse of this triangle, we can just use Pythagorean theorem. So V total squared equals Vx squared plus Vy squared. So our V total is equal to the square root of 20 meters per second squared plus negative 49.5 meters per second squared. And when we put that into our calculator, we find that the total velocity of this dummy is going to be 53.38 meters per second.